Hello everybody, I'd like to welcome you to my talk Advanced Pasta Threat. My name is Paul Litvak, and in this talk we will be speaking about threat actor usage of open source offensive security tools, also known as OSTs. So the agenda will be as follows. We will first introduce what are offensive security tools, and we will also speak about the debate going on over Twitter, whether the publication of OSTs is beneficial for security or not. We will then look at how OST adoption looks like by threat actors, and we will then unveil the OST map, which is a connection graph that we've built over hundreds of libraries to connect between threat actors and usages of open source OSTs. We then wanted our talk to be actionable, so we will see how we can turn open source against threat actors using them. So as I said, my name is Paul. I work at a security company, at a startup based in Israel called Intezer, which specializes in genetic software mapping. I specifically specialize in researching and discovering Linux malware. I've written in the past about Evil Gnome, which was employed by the Gamerodon group, about a couple of botnets targeting Linux systems such as Kaiji, Watchdog, and a few others. And I also built a few OSTs on my free time, so I have some background related to the OST debate. So what are offensive security tools? Well, we can say that these are tools or functionalities which are meant to facilitate intrusions into systems or network or bypass security measures in order to do so. You might have heard of Metasploit, MimiKatz, Cobalt Strike. These are all very well-known OSTs. But there are many hundreds of more open source offensive security tools published on GitHub, and their number is only increasing. You probably have seen this string for this disclaimer for educational purposes only if you've visited some OST projects in GitHub. But as we know, this isn't really the case. Threat actors don't really care about those funny disclaimers. For example, we have Turla, who moved 2 years ago to start using Metasploit in the beginning of their infection chain. And we know that this allows them to, first of all, outsource the development of Metasploit to the InfoSec community. I mean, these guys aren't opening pull requests to the tools they're using. And it also allows them some anonymity, because if the infection somehow fails, if they get caught in the beginning, then they just pull out and all that's left are the artifacts of Metasploit. But it is a generic tool. Everybody can use it. So it really hurts attribution and allows Turla to kind of exit the operation with without letting the defenders know what hit them. And we also had an interesting attack on the Australian government back in June, which were called the copypaster compromises, due to the heavy use of open source offensive security tools, where the attackers just copy pasted tools from GitHub into their tool set, and this allowed them to really outsource almost completely their tool set to open source ones. And this was also an advanced persistent threat, and it is rumored to be China. So the rise of we have seen open source OSTs on the rise for a couple of years now. Back in 2015, one in 20 vendor reports had a reference to an OST project, to an open source offensive security tool. But we've seen this number rise to 20% of all security vendors referencing some OST, some open source OST in their reports. So that's 1 in 4. So we're really seeing an increase in the usage of open source offensive security tools. And as the use of these tools has become more popular, many security industry leaders now believe that the effects of these tools is now a negative over our community. They believe that the free publication of these tools arms intruders and allows them to outsource their research and development efforts to the InfoSec community. So they're just doing intrusions. They're really saving up a lot of resources by doing this. But on the other hand, there are leaders, also security, other important names like Grok, who believe that we should let OSTs be published as they are right now, and just let the status quo be as it is, because because the advantages of releasing OSTs outweighs the disadvantages. Those who believe that releasing those tools is beneficial for our community believe that the advantages that we give for white hat hackers are much more, for white hat security researchers, outweigh the disadvantages that we give those threat actors. They believe that the educational value that we give through the releasing of these tools, especially to newcomers who use those OSTs to enter the industry, is really priceless. Those newcomers won't be able to, who sometimes aren't able to afford expensive courses in order to join the industry, just can go to GitHub and read source code and educate themselves. Furthermore, those offensive security tools allow us to advance the state of the art by allowing researchers from all around the world to build on each other. That means they can incrementally improve offensive technology by reviewing current state of the art and just incrementing its progress. Furthermore, they believe that red teams all around the world are also benefiting from those free publication of OSTs, because they don't have many of red team teams don't have resources to build their own tools. On the other hand, those who believe that OSTs are harming us more than doing good, they believe that arming threat actors does more damage than those advantages which I listed earlier, and that we must somehow find an alternative model by which we must allow red teams and good actors to still have access to those tools, but somehow make those bad actors, those threat groups, unable to really arm themselves and outsource the capabilities to those OSTs. Furthermore, as we gave the Turla example earlier, it hurts attribution. So it really all boils down to the question, is the free publication of OSTs good for security or is it not? Well, I believe we lack data. For example, we do not know how OSTs are useful to threat actors. How many resources are we able to burn by denying them, if we should succeed denying them those OSTs? Another point that we're missing is how beneficial are OSTs to researchers. We only know that some researchers got into the InfoSec community by reading OSTs, by reviewing source code, but we don't know how much. Maybe this is just a small group and it doesn't really benefit in the great view of things. So we need to quantify how good are OSTs for us versus how harmful they are. Another problem that we have is that OST usage information is spread throughout hundreds of articles, and there is no centralized place to track usage of those projects by threat actors. And another problem is that we have little visibility over how smaller OST libraries, such as memory injection libraries, are used by threat actors, because these libraries are usually embedded into custom tools and it is hard to detect their usage. So many security vendors do not dive into the samples deep enough to understand what open source projects power them, or they just don't notice. So overall, we need to know how would these points change if we were to change the model by which OSTs are published. For example, if we moved OSTs to some kind of paywall, how would this really harm threat actors, or would they be able to somehow mitigate this model? And would we still be able to help independent researchers and newcomers or not? So these are all questions that we need to answer. And specifically in this talk, we set out to answer two of these questions. We wanted to, first of all, shed light on which OST libraries are powering custom malware implants, because there was little literature about this topic. And we also wanted to create the OST map, a centralized location for people to track what malware uses which open source projects. So really, how are OSTs incorporated? How do we build malware with OSTs? Well, generally, we saw that there were three types of builders, of open source incorporators, say. So first of all, there was the lazy or inept copy paster. These people, these thread groups just went over GitHub, just selected whatever project they are. They want a memory injection library. Well, they just selected it with their mice counter. That's how I'm imagining it. Control-C, Control-V, enter the code. Just plug and play, use it as an API. And we can see that this is how they build their code, because many times they forget to remove incriminating strings or incriminating artifacts from their code. For example, here we see example of Ocean Lotus. It's an Vietnamese APT which forgot to remove strings from UACME, from the UACME library, which is a library for UAC bypassing. And this is very useful for us as defenders because we can just sign those strings and find malware ourselves. We don't need to really hassle too much about custom malware. And another symptom, I'd say, of malware which is copied just blindly is that many times it just doesn't make sense. You might have heard of the term cargo code programming, where programmers just copy paste code without really knowing what it's doing, and they're trying to call functions and they don't really understand what's happening behind the scenes. They just trying to get it working. And we can see, like in the tweet that Firefox, the creator of UACME, when he was analyzing a sample of Nofter, it's some Windows malware. You say that the malware which copied his code from his library makes little sense because it's just copy pasted stuff and tried to just make it work somehow. So this is the symptoms of lazy copy pasting. And here is another example by 5 groups, some really high profile groups. This was the improved DLL injection library, and they forgot to remove a couple of strings, which you can see in the lower side of the presentation, the strings which they forgot to remove. On the upper side, you can see the strings that we found in the families. On the right side, Dark Hotel, WinNTI, Ramsey, Trickbot, Lazarus. And you can see that these groups forgot to remove those 3 strings because they just probably copy pasted the code without too much analyzing it. And this again allows us as defenders to easily find those malware, but for these groups they removed it pretty soon. Trickbot and Lazarus removed those strings pretty soon after they noticed that they're getting detected because they forgot to remove the strings, but they still use that library. So here's another example of GantCrab using the reflective DLL injection library, and they forgot to remove an export, not a string. And as you can see in the IDA screen, we have the export screen, and we're able to notice that this file has a pretty suspicious export, which we again can sign and find malware like this easily. So the second type of copy pasters of OST incorporators that we have, it's a little bit more advanced. Like we're seeing these groups, they're starting to read the source that they're copying, they're changing it, they're adding some Parmesan on top. And a good example is Carbanak. Carbanak's source code was leaked back in 2018, and it's allowed us a glimpse into how the threat actor thinks, how he builds his code. And for example, this is a library that they have incorporated into their code. It's called TinyMeterpreter. It's a replacement for Meterpreter's initial stager. And we can see that Carbanak took the source code written in C, turned it into C++, did some changes, customized it, and that's how it now looks like in the Carbanak. So this requires the threat actor a deeper understanding of the tool, of its protocols, and really we don't really see mistakes there as much as we saw in the last type of copy paster. And it is harder to detect the usage of this code because once again it's written in different languages, so in the binary we really see big differences, so it's hard to notice. Now the third kind of actor is the third kind of OST user are users who are using frameworks and tools which you may find in GitHub, such as Metasploit, MimiKatz, all kinds of C2 frameworks, which don't require you to use your own custom tool. you just deploy the tool as is, for example, MimiKatz.exe or metasploit.exe, and you just use it because it really offers a large amount of functionalities which probably suits all your needs. So here is me Googling C2 over GitHub, and you can see the amount of responses that I got for C2 frameworks, and the list just goes on. There are hundreds of those as-is tools, which allow attackers a quick iteration of tools, because if one tool stops working, they can just switch over to the next one. They just download the next one, figure out how it's used. It takes 2 hours. They just set it up, and they can infect their victims with this new tool. It's pretty simple, and that is really dangerous because they are completely outsourcing all their capabilities to the InfoSec community. For example, we have this group, this Netwalker ransomware, which got famous around the COVID-19 infection, like at the beginning, because they were using COVID-19 lures. And the way their malware looks like is pretty scary, because they're using almost completely open source offensive security tools. You can see on the right side a graph, and the only custom tool which they are using is the ransomware implant, the ransomware implant itself, which is very easy to build. It's just a file. It's just locks your files. No real effort in building a ransomware tool. But the real research and development is actually in those lateral movement tools, in the defensive agent, privilege escalation, credential access. All of these categories, they're just outsourcing to the InfoSec community. So you can see how harmful these types of malware are. We just outsource their R&D completely to InfoSec community. So it is also important to note that not all code reuses OST. For example, we have here a Stack Overflow question over how to add an application to startup via the registry. So this is actually an answer. I added here the answer on the lower part of the screen, and we took this piece of code, and in Intezer we specialize in genetic software mapping, as I said. So we have our own code reuse engine, and we have a lot of samples in our database for which we compare them against the code that we can notice if there's any reuse there. So we took this specific code and we compiled it, and we were able to notice that Matrix Bunker, Animus Locker, Aurora Ransomware, Strong PT, APT, they all use this specific Stack Overflow answer. But this does not make this question, this little snippet of code as offensive. It isn't an OST because it wasn't meant to be used offensively. We must make the distinction that some code can be abused offensively, but its purpose is not offensive. So that would not be an OST. Is a Stack Overflow question or an answer can even be an OST? That's even a philosophical question, because it's a small snippet of code. But entertain the idea, if a question is purely offensive and all the code that is answered is also completely meant for offensive purposes, is it an OST? Well, again, it's a philosophical question, which I do not have the answer for. We must first find what we regard as OSTs. So at one of the purpose of the talk was to find which malware was using which offensive open source tools. So what we wanted to do is really create this huge connection graph, and figure out. So if we go, for example, if we want to find out which open source Lazarus used, we would go to the map and quickly see it in a centralized location. So to do this, we had a lot of hundreds of articles which describe already what kind of open source tools those threat actors are using. So we did use them. However, we found out that the information there was lacking, because there were a lack of OST libraries, such as memory injection libraries, credential access libraries, which those threat actors, which those vendors were not really documenting. They were usually documenting those frameworks, those bigger tools, which were much easier to document. If you see a MimiKatz exe, you just write it down. It doesn't take a lot of analysis effort. But we were interested in those tools such as the reflective DLL loader and all of those OSTs, which contain offensive functionality but are really underappreciated by security vendors, and they are harder to notice. So we came up with a couple of ideas. How do we find those those libraries, those more subtle connections? So our first idea was to find library strings such as the one we showed Freakbot, Ramsey, and Dark Hotel using, but those strings, those are mistakes. Those are symptoms of lazy copy pasting. But we know that not all actors are lazy, and even those who are lazy, it doesn't take a lot of effort to remove strings. So we knew that this tactic would help us create find some connections, but it would not really be good enough for a really purposeful graph. So this would not work. Our second idea was to find perhaps some unique strings, some unique constants. For example, the reflective loader export in the reflective DLL injection library, all kinds of unique properties for each project. But we soon found out that this wasn't scalable, because for each project we would need to review its source code, really figure out what's unique about this project, and then sign those specific unique artifacts. And then we would have to make sure that these are really unique to this project, and we might find false positives, and we might discover that they were also used in other projects. So this was again unscalable for one man to do. So my third option was to use a code reuse engine. As I said, at Intezer, this is our main strength. We have our own in-house engine. But this also imposes a couple of problems. For example, code varies between compilers and different flags used. When you take a binary, you have to really disassemble it, and then you compare the binary patterns to another file, which for example would be the library. So we would compare code from Lazarus, from a security report, to this file that we compiled, is for example the reflective DLL injection, and we need to make sure to somehow normalize the code between them. So our code reuse engine is pretty strong, but there are still some problems. If you had compiled the program through an older compiler, then different code would be generated, and that would be and then we could miss some stuff. And another problem was that code varies through time. If we took this reflective DLL injection library, for example, from 2010, it would look completely different to 2020, because code changes. There are commits made, and we can see this in Quasar that the author had made like 10 commits in the day, and you can see on the right side how many commits are being made throughout the years, and code constantly changes. So we needed to somehow pay attention to these changes, and the way that we really overcame this is that we built our own pipeline to create as much code as we can from each library. So our plan was to take all those libraries that we compiled, those code items, and we would try to compile the library as much as, and we would try to generate as much code as we can from the library, and then we would take the code and compare it through our code reuse engine, and that would be how we would create the graph. So what we came up with is this project that we open source, and you can see it in the presentation, where we go over projects, over each monthly commit in each GitHub project. We download the commit, and then we compile it through about 7 compilers, through Visual Studio 2010 up to Visual Studio 2019. And then we compared it to our code reuse engine, and then that is how we were able to really create the graph. So for example, if Lazarus used in their code the improved reflective DLL injection from a version of 2015 compiled with the Visual Studio compiler from 2019, we would find it, we would notice it, because that's how we built our pipeline, to really account for all these changes throughout time and throughout compiler versions. So overall, we compiled 80 libraries, 80 offensive security tool libraries, and we also added 29 non-native tools written in PowerShell, Java, Python, which our code reuse engine did not support. And these libraries and tools, we also used we used security vendors ongoing, existing reports to map out already known connections, because some of these samples we were not able to find in VirusTotal or through other well, sites like VT, because sometimes security vendors do not publish all the IOCs to VirusTotal. So we added documentation which already existed to make the connection graph stronger. So now I will demo you the map. So here it is. As you can see, blue stands for library. For example, this is here. If we click this is the lasagna library, the credential stealing tool. And we see here red nodes, yellow nodes, and also, oh my god, mouse is running crazy. And there's also orange nodes. So as I said, blue is library, red would be APT, and orange would be notable threats such as TrickBot, DNS Birthday, Carbanak, actors which are not advanced. Well, they're not really government backed, but they're pretty notable, and they're very known within the InfoSec community. And on the green, there are also other documented threats, but they are not that known as much as the orange ones. So as you can see, we can look for our favorite threat actor, for example, APT10, and we can see all the libraries that it had used. For example, here we see it used Coadic, custom MimiKatz, Impacket, HTran, Remcom, and we can then switch to, for example, click Empire, and we can see all the threat actors which used Empire, and we can keep on going. For example, we switch to GentCrab, we see that it used reflective DLL, and this map really shows to what extent threat actors are using offensive security tools. And we welcome you to review this map yourself. There's no point in going per each threat actor. That would be a blog by itself. But we also have a GitHub repository where we welcome you to add your own contributions. If you find this threat actor uses a new library or some undocumented offensive security tool which we did not add here, we welcome you to add connections to GitHub, and we hope that this map will be a centralized location to really track the usage of these tools by threat actors. So as I already showed you an example, but this is the reflective DLL injection. We had little before creating the map. There was little information known about threat actor usage of generally memory injection libraries. This information was just largely ignored. These libraries were largely ignored by security vendors, as I said earlier. So here's an example of the libraries that we found that were using the reflective DLL injection, which most of them were undocumented. So we really had a lot of success in creating the map when it came to those smaller libraries, especially memory injection, credential stealing tools, and so on. And this is another cool example. We found that Hackbit ransomware stole code from async run C#, C2 framework, a RAT OST tool you can find in GitHub. And specifically, this ransomware only took the anti-analysis modules, the anti-analysis code from this library. So you can really see the power code reuse enabled us, how granular were the connections. We were able to find really even if a function was stolen from a piece of code or a piece of library. So finally, we wanted this talk to be actionable, so people could see what we can do with open source and how do we turn the tables against threat actors. So here for example, is the memory module library. This is a memory injection library, and you can see on the right side how the assembly looks like for this library. Specifically, this code, all it does is it's a memory injection library. So this takes the memory, the DLL or whatever that it tries to inject into memory, and it verifies its MZ headers, its all its headers that the file is the file that they're trying to inject is really a PE image. So here, for example, what it does is you see it takes image.signature, moves it to EAX, and compares it. Basically, it checks that the header is okay. But if not, then it goes here to the left side. It calls the setlist error API, Windows API, with a value of 0C1H. So if we want to reverse this file in a different, if we want to reverse this library in some different file, we would clearly easily notice that this was memory module, because we now know how memory module looks like. But we don't really know how we can contextualize this knowledge, how we can crystallize this knowledge of how the library looks like into an effective rule, into a textual rule, so we don't have to reverse each sample manually to really figure out that memory module is there. So what we did at Intezer is that we took all those libraries that we compiled in the compilation pipeline that I showed you earlier, and we analyzed those files for repeating binary patterns, because in this example, we always know that there will be a move ECX 0C1. I mean, there will always be this setlist error API call, and before that, a move with a constant value. So we were looking automatically for all those repeating binary patterns between different versions, and then we took those specific binary patterns that matched between each library, because they would be very strong. They would be very convenient for us to find. They repeat in every version between each compiler, and we created an automatic signature, and we also open sourced all those signatures that we created, so you could use them, deploy them, and hunt for malware yourself. And these are results. We found, for example, load detected Lazarus files and load detected Carbonac. Carbonac was using memory module. Lazarus used the improved reflective DLL injection. We saw the strings earlier, and we were able to find them through code reviews, through those Yara signatures, which were built on binary patterns. And we were not looking for Lazarus or Carbonac specifically. These were just libraries. These were just threat actors which used those libraries, which was very nice for us, because we weren't looking for APTs or other for any specific family, that is. And we wanted this technique to be applied at home as well. You don't need a big engine such as ours to do this. So we also published a blog into how you turn those patterns, those binary patterns, manually into Yara yourself. So I invite you to check our blog, and it will be much more technical than this talk. It involves how you reverse engineer a library and figure out how you build a signature by yourself, so you can deploy it and find Lazarus. So it all boils down to what is the future for offensive security tools, and the answer isn't simple. It's really up to the community. Currently, the solutions which are proposed, in my opinion, are pretty weak. For example, there is one solution, a pretty popular one, which proposes that OSTs are put through some kind of vetting program, like a friend brings a friend, and this would make threat actors unable to really get those OSTs, and those OSTs would fall into wrong hands. But the problem is there's one bad apple in this vetting program, and all those OSTs will be released, and threat actors will have them. So this model is pretty fragile, and there aren't that many solutions, because right now mainly awareness is being promoted regarding this OST issue, and those who are opposed it are trying to really convince the community that their approach, that the status quo is fine, nothing's bad. I mean, it's it's beneficial, is what they claim. So currently the battle for awareness is going on. I also believe that we must consider ROI when we're speaking about OSTs. We shouldn't think about it as black and white. We need to think about each category of OST and whether it is beneficial for the community or not. For example, memory injection libraries, I believe, are mostly beneficial for researchers, because they don't make the development process for the threat actors more easy, unlike tools which can be deployed as is. Threat actors really need to figure out more stuff, to invest more into implementing, into incorporating libraries in their code. And we saw that when they do it lazily, we can find those libraries. And another example for a good example for OSTs which are more harmful are C2 frameworks, because they usually aren't very educative. We have already so many dozens of them, and I think even hundreds, and we don't really gain new insights by the release of new C2 frameworks and post-exploitation frameworks. So we must really consider the ROI for each category on each library, and we should not treat OSTs as all the same. And perhaps we should think about this when we are proposing solutions, that we shouldn't ban all OSTs, but we maybe need to think about the publication of C2 frameworks or post-exploitation. Finally, I'd like to call for action. If there are OST offers in the crowd here today, well, I would suggest you add fingerprints into your OST projects, so defenders would be able to sign on those fingerprints and defend their networks. For example, this is a tool that I built called the Glory Hook. It is a hooking library for Linux, which allows you to take two files and merge it into one. But the problem is that this library can be used offensively as a file infector. So to offset that threat, I added a string. You can see here, I added these symbols, the string into files which are generated by my library. So if it is used offensively, then defenders would be able to find those files more easier. They would be able to create a signature, a YARA signature on those files which are created through the project. And I doubt that threat actors will notice this until it's too late. Another suggestion is to turn bigger OST projects into sponsorware or grace period, because if there comes a new version of your OST project, then defenders' signatures may break or stop working. So a grace period allows defenders to readjust and build new signatures for your projects, and I think it is a win-win for everybody. So finally, I believe that a lot of non-technical assessment is required. We need to think of alternative models, such as the vetting program models, which are different to this, and we need to think of incentives for OST offers to go along with our solutions, because currently there are some advantages to creating your OST framework, because it's a proof that you have offensive knowledge, and it helps with finding a job, and it's fame. You get a lot of GitHub stars, and it's fun. So we need to think of incentives to convince OST offers to really understand the issues of publishing OSTs freely. And we need to think about the effects of these models over those questions that we raised earlier, as how we will be able to still support independent researchers, newcomers, and still hurt threat actors. Finally, we published the OST map, and we welcome you to create contributions at our GitHub page at github.com Intezer OST map. And we hope that our technique for hunting OST libraries will be beneficial for defenders. I'd like to thank you for attending my talk. My name is Litvak. Thank you very much. Good day.